Pythagoras, Bernoulli, Euler, and Taylor. Though they're best known as influential mathematicians, their other areas of interest all converged on music. In fact, Pythagoras considered music as another branch of mathematics. But how are the two related? Music is considered an oscillating function, making it easy to model. Pure tones are the easiest, since they're simple waves represented by a single trigonometric function, like sine. The frequency and amplitude of the function determines the pitch and strength of the sound respectively. When these waves travel through the air, the pressure waves oscillate your eardrum, creating sound. But pure tones aren't the only sounds that exist, and one simple trig function can't model everything. This is where Fourier series come into play.
So, what is a Fourier series? First, let's go over what a periodic function is. A periodic function, such as a sine wave, comes back to the same point every cycle. So for sine of x, you'll reach the exact same point every 2 pi. Common examples of periodic functions are functions such as square waves. Now, what if we wanted to approximate or graph the square wave function, a waveform commonly used in electronic music? If we just use f of x is equal to 4 over pi sine of x, that's a pretty bad approximation. But if we add another sine function at a slightly different frequency, then we get a slightly better approximation. Now, if we add an infinite amount of sine functions at different frequencies, we get a pretty good approximation. What if we wanted to graph different functions? In that case, we could use the general formula for the Fourier series, incorporating both sine and cosine functions. So, in the simplest terms, the Fourier series attempts to model a periodic function by adding together a bunch of trig functions at different frequencies, and it can model almost anything. It can even make art.
Now you're probably wondering, how does this translate into music? Fourier series allow us to make complex tones by simply breaking down complicated sound waves into similar components. By stringing a sum of sine waves of different frequencies and amplitudes together, we can synthesize sound and create a unique combination of harmonic components that create unique sound qualities that give us the audible differences between a trumpet and a piano. The differences in sound, or timbre, of each of these more complex tones is due to their overtones, or additions of pure tones on top of the base, or fundamental frequency. Only a sine wave has no overtones. The other waves sound the way they do because of the quantity and strength of their overtones. Though seemingly at random pitches, these overtones, also called harmonics, follow whole number multiples of the fundamental frequency and are often compared to the harmonic series in math. The difference between harmonics and overtones is just that harmonics include the fundamental frequency. Harmonics are integer multiples of the fundamental frequency, which is the lowest frequency allowed by the length of string or column of air. However, it's not the only way that the string or air vibrates. Besides the frequency that vibrates along the whole length of the string, other frequencies that divide the string into halves, thirds, fourths, and so on vibrate at the same time. Thus, every musical pitch is a combination of the fundamental tone and its overtones. The harmonic series forms the basis of all Western music theory. Seemingly coincidentally, the first 5 harmonics of any fundamental frequency will play a pitch that sounds double that frequency, then 3 times, 4, and 5 times. Or in musical terms, the octave, the fifth, the second octave, and the third, respectively, which form a major chord. When the most audible harmonics, or about the first 30-ish, are transposed into the same octave, they closely correspond to 12 sort of equally spaced divisions of an octave. Since the divisions aren't exactly equal, intervals will be out of tune with each other. For example, 2 major thirds on the harmonic series of a C will sound different. The first will have a ratio of 5 to 4 of the original frequency, and the second of a 9 to 7, when a 10 to 8 ratio would be perfect, since it would double the original 5 to 4. So, although the chords on the harmonic series of a fundamental tone will be more in tune or played with just temperament, for more complex music, it's simpler if every chord were equally out of tune, so that every major third sounded the same as any other major third. So going back, if the first octave is found by doubling the frequency, and the most audible harmonics divide that octave into 12. Each note of a 12-note scale is a multiple of the fundamental frequency by the 12th root of 2.
Calculus's influence isn't limited to pure math and physics applications. It's part of the foundations of how we perceive and create sound in art. While the Fourier series breaks down the complicated waveforms into simple trig components, the harmonic series shapes the structure of musical scales and chords. Even though the creativity of music feels separate from the logic of calculus, one could not exist without the other.